recorded. So we're going to go over quiz 3 on behalf of your lesson. Problem 1. We got this crowbar, pipe pin, and it says true or false. The reaction at point A is 0 and force P is non-zero. Well, you look at this and you think, of course it's not 0. I mean, if you put a crowbar, it's probably going to bend at that point. Well, is it though? Because notice that it's pulling straight down. So a reaction force is always going to be perpendicular to the surface. You cannot have it otherwise. Like that. And then we do some Newton. You say the sum of the forces in the X is 0. And we'll take a look at this thing. See that the only force that is going to act in the X direction is r sub A times cosine, nope, sine of beta. Which means either beta is 0 or the reaction force at A is equal to 0. And we're going to assume that theta is not equal to 0. Then r sub A is going to be equal to 0. So this answer is true. It's pretty intuitive, but there is no perpendicular force acting on that. And that's a little hard to get your head around, ain't it? Well, if you're pulling, and it's definitely going to be a moment about this caused by the other reaction forces, and that will cause bending, but there's no reaction force itself. Okay, next problem. Alright. Another true or false. So we got pole, and we got ball. Okay, we call this point A, this point C, this point B, and this point D. false? This is we can find all the reaction forces for the beam. And it's in static equilibrium. And surfaces are frictionless. Alright, let's take a look at the free body diagram for this beam. That means that right now we're going to ignore the circle. The only thing we know about the circle is it's providing a normal force on this beam. So let's do this. We have y, x, the weight c, and a B. That's all reaction B. And we look at that, and we have three unknowns. Y, AX, and RB, and three equations. Forces X, some of the forces Y, some of the forces, some of the moments about A. So let's see if we can use those. It looks straightforward enough. Okay. Let's do the moments first. Some of the moments about A are 0. So then theta. So W times sine theta times the length of C is going to be equal to reaction force at B times the length of B. And this is known, this is known, this is known, and this is known. Therefore, force B is found. And some of the forces, x equals 0, a sub x equals let's see. That's 30. Okay, and the x, it's going to be equal to r b times sine 30. This is now, this is now. And then some of the forces on the y. Y equals W. Another force on the Y. AY plus RB cosine 30 is going to equal the weight. This is now, not 30, theta. This is now, so yeah, we can solve for all the forces here, which means it's true. Hooray! Now, the next problem uses this same picture, but we're going to do it for the ball. And I want you to imagine for me, if you will, if you took a ball, and you took a plank, and you put the ball on a patch of ice, and you laid the plank on top of it, what would happen? Well, the ball is just going to start rolling right out, and the plank is going to go thunk. So, intellectually, this, it's not going to be in static equilibrium. Why did I spell static equilibrium with a G? we have to, but in the first problem, it didn't go as we thought it would. So we still have to, this isn't an intellectual problem, it's a mathematics problem, so let's do this. Free body diagram for the ball. We have normal reaction force at D and reaction force at B. And the weight of the ball. Okay, so the sum of the forces in the X I don't remember how it did this. Okay. Well, so R, not 30, why do I keep writing 30? So yeah, RB times sine of 30 is equal to 0. But we need to stop right there. Normally we would just say RB is 0. Why do I keep saying 30? It's theta. We need to stop right there. Because we already, in the previous problem, looked at RB. And RB does not equal 0. And, I mean, the force is going to have an equal and opposite reaction force. That's what a normal force is. So we know that this is the same RB that we solved for. So either theta is 0 or we are not in static equilibrium. So it's going to be false. We can't solve for the forces because it's not in static equilibrium. Right? I mean, if it was here, I suppose it would work, but that's what he had written on his answer sheet. So we're going to assume that it's not in static equilibrium, and thus the answer is false. Okay, next problem. Where'd it go? Okay. Last problem. We have a ramp here. And finally something that's actually 30 degrees, so I won't be confused. Now we have this block here, which means 1 centimeter tall, no, 10 centimeters. And we have this ball that's going like this. Radius. And 50 kilogram ball. So, radius is 2 centimeters. Can the block stop? No, 2 meters. That's a giant boulder. Can the block stop? No, it's a roller, isn't it? Okay, stop the roller. There's 2 ways to solve it. Let's go, but both of them use the same free body diagram. So let's do that. Free body diagram! Woo! We're going to call this point O, point A, and this point B. We're going to calculate our B, our A. And some of these distances. We know that this is 2 meters. We know that this is 2 meters. What we want to know is this length and this length. So we know this length, this is the thickness, this is 1 centimeter. Or we're just going to call it T for now. So this is also, this is going to be 2 minus T, and we'll call this one X. And we also know that this angle, through the magic of trigonometry, wrong angle. Let me take a look. What we, this angle is 30 degrees. Through the magic of trigonometry. You want me to go through that real quick? It's 30, which means 60. And this is the right angle, so this is 30. And this is our 2 parallel lines and another parallel line, so this is 30. Okay. So then, method 1. We're going to assume it works. And this thing is stopped. And so what that means is in total static fluidity equilibrium, so we're going to just solve for that. So we're going to say some of the moments without point A, because it's not, you can think of it like rolling over the step, it would be rotating about point A, but it's not. So we're going to say that some of the moments about A is 0. And those are, why did that say 30? It should say 2. Hold on. If that's the case, then we have this triangle, which is 2 times T, which is 1, and 2. So we can find this one to be 4 equals 1 plus squared, x equals the square root of 3. I should have known that. 30 degrees. By the way, this is 30 degrees. I just figured that out from this triangle. Okay. So, it's going to be the weight, and I'm going to call this y minus x. So the weight in the y is going to be causing a positive moment, which is counterclockwise. So it's going to be w times e sine 30. Nope, cosine of 30. And its perpendicular distance, which is x. And we're going to also take the x component, which says that which is going to be that's weird. Oh, this isn't 1, it's 1.9. Okay, that's what the problem is my trigonometry. Oh, yeah, you know, 1 centimeter, so that's 1.9. So we have this triangle that's 1.9 meters, and that's x, and that's 2 meters, and so we have 4 equals 1.9 squared plus x squared, and x is equal to 0.62. Let me just check that with my calculator. Yeah, just about. So x is 0.62. And then we have an x direction, which these components look like this and this. So this is going to go on this parallel here. Which means its perpendicular distance is 2 minus t. So then it's going to be causing a clockwise moment, which is negative, so it's minus w sine, sine 30 degrees times 1.9 meters. And then we have the reaction force at B, which is going to be causing a clockwise moment times that distance, which is also 0.62. So we have So we have 0.62 reaction force at B equal to 50 times 9.8 times cosine of 30 is root 3 over 2 times 0.62 minus 1/2 times 9 is, come on, okay, there we go. Is negative 41 newtons goodness. So this is a reaction force, which means because it's negative, it will be pointing in the opposite direction. This means the lamp is sucking in the ball, which is impossible. Therefore, it does not stop the ball rolling. And that's method one. Method two. And equal. The minimum required thickness to stop the roller and compare with given. So what this means is that we're assuming that the thickness is just enough so this ball is only just starting to turn. Not really, just starting to. What that means is that this point B is just starting to lift off from the ground, which means that reaction force at B is going to be 0. So, moments. Sum of the moments about A is equal to 0. 0 is equal to weight times cosine of 30 times that perpendicular distance, which is x, minus w sine 30 times its perpendicular distance, which is 2 minus t. And we arrange this, we cancel, we get cosine x cosine 30 equals 2 minus t sine 30, divide by sine cosine and then 2 minus t, you get x over 2 minus t equals the tangent of 30. And we also have an equation relating x to 2 minus t, because remember this is 2 meters, this is 2 minus t, and this is x. So we know that 4 is equal to x squared plus 4 minus 2t plus t squared. That looks terrible. And this is 2 minus t squared. So that x squared equals 2t minus t squared. Plug that in, we get 2t minus t squared over 2 minus t equals the tangent of 30 degrees. And let's see. What's going to happen is 2t minus t squared equals to t times 2 minus t. Those two t's cancel, and so we get t equal to tangent of 30 degrees, which is equal to 0 point. Okay, that's not right. Or did I screw up this time? weird. Oh, okay, I know why. So, we get 0.57, which is 57 centimeters, which is much bigger than 10 centimeters. Therefore, it will not stop. Remember your units, or else you might get confused. Okay. And that's your quiz. So I hope this was helpful. See you next time.